It is my pleasure to introduce our next speaker, Michael Plummer. He'll be talking to us about a harmony of clouds, chemistry, and aurora, vertically mapping the atmospheric waves of an isolated planetary mass object.
Good afternoon, everyone. This is the penultimate talk for today, I believe. Appreciate everyone's time. I'm, like you said, Michael Plummer. I'm an assistant professor at the United States Air Force Academy, and I'm going to talk to you about my favorite brown dwarf / isolated planetary mass object, and essentially its weather and space weather. But before we get going, I'd like to start a little closer to home and talk about Jupiter, because it's essentially, we're talking about solar systems and how exoplanets, we can learn from that, but also we can learn about brown dwarfs from the closest thing we have to a brown dwarf in our solar system, Jupiter. So if we look at Jupiter's atmosphere, we see a dynamic atmosphere. We see storms that have existed for hundreds of years, regions of upwelling, downwelling, clouds and waves. We even see strong auroral emission. So it's thought that brown dwarfs and low-mass brown dwarfs and isolated planetary mass objects might harbor similar mechanisms. In particular, I've mostly been working on the past year or so on SIMP 0136. It's a nearby planetary mass object, about 10 to 15 Jupiter masses. Has a temperature of about 1150 Kelvin. That puts it in the LT transition, which I'll talk about here shortly. And it has a rapid rotation rate, so it rotates every 2.4 hours, which means that we can, with a very short amount of observation time, we can actually get a picture of the entire longitude. Yeah. It also has a very strong magnetic field at 3,000 Gauss, meaning that strong magnetospheric processes are a real possibility. So brown dwarfs and planetary mass objects near this LT transition object, or LT transition at about 1300 Kelvin, have a history of very high variability in the near infrared. Not only is it variable in terms of percentage, but that variability is variable in itself. So what could cause this variability? Well, we think that it might be atmospheric dynamics, in particular clouds. You see, because brown dwarfs can't fuse hydrogen, they gradually cool throughout their lifetimes. As they do so, from about 2500 to 1300 Kelvin, this is the L class for brown dwarfs, it's thought that clouds form in their atmospheres. For SIMP 0136, we think that means an iron cloud deck with an overlying forsterite or a silicate cloud layer. Then at around 1300 Kelvin, it's thought that those clouds begin to rain out, creating a patchy or inhomogeneous cloud layer. But there's been other alternatives for what's causing this variability. One is aurora. This might be something similar to what we see with Jupiter, where we have aurora powered by plasma from Io, the volcanic moon. Or it could be double diffusive convection or fingering convection. You can think of this as regions of upwelling hot carbon monoxide and downwelling cool methane. Trying not to press the button that turns everything off here. To understand which one of these processes is really controlling and dictating the variability, we look at two different observations, JWST observations of this target. It's taken about 35 hours apart, so with a 2.4-hour rotation, that means that there's about 15 rotations between the two. And here we're just looking at light curves bend in 0.2 microns from about 1 micron to 2.8. And we can see essentially that there's three characteristic shapes here. The deeper wavelengths, the shorter wavelengths, are usually best fit by a three-wave model and are generally more complex. And then we have normally a lower order harmonic, longer wavelengths, and then a kind of intermediate layer. You can see that longer wavelength region actually evolves significantly from the first observation to the second. So we're seeing a really dynamic atmosphere. But I think we can better picture what these wavelengths mean for the actual atmosphere if we use, press the wrong button, if we use a atmospheric model. In this case, we're using Sonora Bobcat, which was developed here at University of Arizona by Professor Marley. And what this is showing is for every wavelength, the corresponding pressure where most of the flux is coming from. So you can tell it basically is a way to map wavelength to pressure, with going up in pressure is going up in altitude. So if we convolve that with those light curves, what we get are these vertical, what I'm kind of calling vertical flux variability maps. And what these are mapping is it's mapping the variability at different layers in the atmosphere. You can see on the left, for the first observation, we have variability of about plus or minus 1.5%, while on the right, we have variability of about plus or minus 1%. Other key features are we see that the deepest layer has that more complex behavior. And we kind of interpret that as the essentially the troposphere or the weather layer. And then you kind of see it's kind of hard to see kind of a fuzzier layer, and we think that's essentially the top of the clouds, which causes a muting and kind of decrease in signal to noise. And then you see a upper layer, which is generally lower harmonic. You can see for nearest there's a little bit more structure, and that's because it actually extends to longer wavelengths and higher altitudes. So we can learn more by looking at specific wavelengths. In this case, we can look at wavelengths corresponding to foresight. And what we interpret these are modulations due to clouds. You can see that's essentially kind of a two double peak cloud in the first one and a single in the second. And that cloud modulation appears to be tied to molecular absorption variability. In this case, we'll look at molecular absorption in carbon monoxide, water, and methane, essentially where the dark regions here indicate regions of enhanced absorption and bright is less absorption. You can see that carbon monoxide and water are anti-correlated with clouds, while methane is correlated with clouds. So what could be causing that sort of difference between the two? We think that the solution might actually be essentially in the equation for the formation of foresight. You can see here that water is necessary and is essentially consumed when you're forming those clouds. So the idea is that when you're consuming that water, you're pulling oxygen out of the atmosphere. And when you're pulling that oxygen out of the atmosphere, carbon monoxide is no longer the preferred carbon reservoir for carbon, I guess. So what would be the preferred reservoir? The idea is that that would probably be likely methane. So that's why that's what at least the first order solution. There's some other complications with temperature as well, but that is, sorry. And that's what we think is going on here with the difference between the anti-correlation between carbon monoxide and methane corresponding to that cloud layer. And this would be time-resolved, time-varying carbon disequilibrium chemistry. I also mentioned that there's Aurora, that we may see some signs of Aurora, and so we wanted to see if there was any signatures. So I'd like to call your attention again to that low altitude methane absorption feature, which is with a periodicity driven by that cloud formation. And you can see that that's effectively prominently at lower altitudes, about 1 bar. And you can see that the higher altitude methane has the same periodicity, but now the sign's flipped. So essentially what we think is going on there is that that absorption feature has been flipped up to an emission feature. And the only thing that could do that would be some sort of heating source. So based on some other, based on the 3000 Gauss magnetic field, and as well as a temperature inversion detected with the same near-spec data by Everett and Essikin, we think there is a chance that this is a auroral signature, but could also be something such as gravitational waves. So I'd like to acknowledge some of my external collaborators from Montreal, McGill University, Boston University, and Trinity College Dublin. And with that, I'll leave you with my takeaways, and you can see this is actually not this paper. This paper should be out here soon on the archive in the coming weeks, but this was my last paper on the same target.
Questions for Michael? One in the back.
Hi, Jorge Sanchez, ASU. Excellent talk. I was wondering, you mentioned you guys use the Sonora Bobcat models, but I know you also mentioned you were interested in understanding the role of things like disequilibrium chemistry or cloud formation. Do you think, can you comment on the use of like using other models in the Sonora series that would include the disequilibrium chemistry or the clouds, see if you can get a handle on that?
Yeah, essentially my plan is to build a nice appendix where I go through it, pretty much all the different Sonora, Diamondback, Alfal. I think if I did if Bobcat, Diamondback, and Alfal, that would probably pretty much address it. I have compared it to retrieved contribution functions. Trick with petite retrans, specifically the ones that was retrieved for SIM0136 in Nesetkin 2025. The trick with using, like you're saying, I do think that's the correct way, is to use the Ford models for these, just because of the complexity of the chemistry, is you're going to lose that when you go to a retrieval model, because usually there's simplifying assumptions with the carbon, the methane, and quenching and things like that. But yeah, that's definitely something that's like I would like to have as like a nice appendices, if that makes sense, where you can see all of them.
We have time for one more question for Michael. If not, I'll ask one.
Okay.
This is really exciting results. This is what the brown dwarf community has been waiting for JWST to do at the LT transition. This was so hard to do from the ground for so long. Are you looking at other objects to do the same sort of analysis?
Yeah. I mean, I would definitely. I'd suppose I need the data first. So I'm on a couple of teams. But yeah, anything that I think we could do any sort of these maps with and kind of look for these connections. We just need the time resolved spectra. So it'd have to be a bright enough object that we'd have a lot of signal to noise. Because if you notice on these ones, to get the I don't know if I can go back. Maybe this is off. But anyways, to get the signal to noise was, you have to like bend down the time quite a bit, and you have to do these big. You actually have to bend across the entire spectral region to get the molecular one to get. That was the biggest trick, I think, with this, was actually getting a good, like, serviceable signal to noise. So I mean, SIM0136 is a pretty bright object, so you would need something probably similarly bright, or just more time, or maybe stack multiple. Like if you had I'd really like to do it with, like, sorry, I'm getting carried away, with like some of those late T-Dwars that have like 1 hour rotation periods, and maybe you could assume that it doesn't change much over one rotation. And then if you could stack those, I bet you could get pretty good maps.
Awesome. Thank you. Let's thank Michael one more time.